So let's review dislocations. Again, I want to remind you this is just a review of what we talked about in class and is not a replacement for attending lecture and learning the content. But because there's no textbook, this is a way to review what we talked about. So we talked about dislocations and introduced them from the concept of plasticity and plastic deformation in highly ductile materials, for example, metals. And in those cases, you can imagine having a block of material and you're shearing it. You have some force that's being applied. When you have that force being applied, you can think about all of these planes pushing past each other. And when that happens, all the bonds between the planes have to break and simultaneously shift and rebond. And that's analogous to moving a rug. You move a rug, you pull on the rug, you have to overcome the friction between the rug and the floor, and that's going to scale with the area. What we find is that the calculated force necessary for plastic deformation is about 100 times less than what's actually observed. And the way that we can think about this is that there's some other mechanism, and in this case, it's dislocations that are making it easier. In the analogy of the rug, instead of pulling on the rug, you have a wrinkle that you put in the rug, and that wrinkle rolls along, and when it gets to the other side, it disappears, and the rug has shifted by a couple centimeters at the most. But if you put lots and lots of these wrinkles, you can actually move the rug across the room. And in the same way, if you have a piece of metal and you bend it, what you're doing is you're having tons of dislocations that are moving a little bit at a time. And when I say a little bit, they're introducing several angstrom worth of displacement, but you have so many of them passing that you get this macroscopic plastic deformation. Now, the picture that we drew in class was a picture in which you had a part is being stressed. The stress results in a dislocation and the little edge. So this dislocation kind of squirted into the middle from the edge and is sitting in here. In our representation, we said, okay, we got some extra half plane of atoms sitting there. These atoms that are sitting above the dislocation, because there's an extra plane, they are necessarily have a bonds are a little bit shorter. So these are all feeling compressed. Down here at the bottom, you could say, well, we're missing half a plane of atoms instead of saying we have an extra one. And these bonds are all stretched a little bit, therefore they are in tension. They're feeling a little bit expanded. And this dislocation, just like the wrinkle in the rug, you push it and it's going to move with a velocity. This has a velocity and it's cutting across the block, and at the end it pops out the other side and we wind up with some macroscopic strain. And each time one of those passes, it advances the strain. The amount of strain that's left after a dislocation passes is characterized by the magnitude of this Berger's vector. The Berger's vector. And I'll show you that in an atomic model shortly. That's one of the two vectors that we use to characterize a dislocation. One of the Berger's vector, which is the strain associated with the dislocation, and the other is called the line vector, and the line vector is parallel to the dislocation at any point. So L, we oftentimes use a lowercase l to describe that. L is our line vector. So here I've drawn a picture of a dislocation. It started at this edge, and it threads through and it comes out the backside of the part. Now, everywhere along that line, the line vector is running tangential to the dislocation. But the Berger's vector is constant. And the reason the Berger's vector is constant is that when this dislocation, you know, say it started here, when it pops out the other side, it has the same displacement kind of everywhere on the dislocation line. So the Burgers vector is constant, and the dislocation line L changes with the line as it threads through. So if you just think about that, that means we can have kind of two extremes. We can have one extreme in which the line vector and the Burgers vector are 90 degrees to each other, and we call that an edge dislocation. And the other extreme is when the line vector and the Burgers vector are parallel, and if the sign is not important. So we can have L like this, or we can have it like that. That's not important. Same thing, if you imagine our edge dislocation, we could simply reverse the direction, and it's still an edge dislocation. But most of what's happening here is actually a mixed case where the line and the Burgers vector are not exactly pure edge or pure screw, but a mixture of the two. And the good news for us, because we described what's happening around the dislocation in terms of the elastic strain, and because most of the time we can work within linear elasticity, we can simply take this mixed dislocation and talk about it as being a sum of the edge and screw components. So we can look at these a little bit. This is our edge dislocation. In this, dislocation is sitting here, so our line is this way, and we can draw a circuit around this. So starting here, we're going to go 1, 2, 3 to the left, 1, 2, 3 up, 1, 2, 3 to the right, 1, 2, 3 down, and we don't close the circuit. We're actually off by this much. So that is characteristic of the Burgers vector. So in this case, the Burgers vector is here, and the line is here, so they're perpendicular to each other, and that's why this is an edge dislocation. In contrast, this is our screw dislocation. So here, the dislocation line is in this length direction. And now, we'll put a little to the side, let's draw a circuit. Let's draw a circuit. We'll start here. So I'm going to go 1, 1, 2, 1, 2, 1, 2, and then 1, and it should come back, but it doesn't. You see this? Drawing the circuit around. It doesn't. And this displacement is our Burgers vector. So the Burgers vector is in parallel to the line vector, and that's why we call it a screw. And another reason we call it a screw is if you think about this and tracing around here, it's a lot like a spiral staircase or the threads of a screw. So you can think of this as a spiral staircase type dislocation, and it goes all the way around. And in fact, as we circle around, if I were to circle around one more time, then the next time I make it through the circuit, I would be here. And if I go circle one more time, then I'd be here. So each time that I pass around the dislocation, I advance by one, well, put it this way, you think of it as every time I go around, I advance by one stair step. I'm going up the spiral staircase. And that is our review of dislocations.